Hello, everyone. I'm going to be talking to you today about linear functions. A lot of this is review from your Algebra 1 days, but this is a super important topic, and it is extremely heavily covered on your SAT. So these are things that you're really going to want to pay attention to and make sure that you ask questions if you have them. Okay, so sorry. I didn't have my pencil ready. Here's a little warm up for you. Allie currently has $25 and he's going to start saving $5 every week. So we're going to write an equation to model this situation and we're going to figure out if it's a function. Now, there's a couple of ways to do this. I've told you before that I struggle with writing equations sometimes, but there are certain characteristics that this statement has that I recognize right away. Okay, this is the first thing right here. He currently has $25. So that is what we call an initial condition. And I'm going to talk to you about that a little bit more on the next slide. Initial condition is where this whole thing is starting from. So it's $25 as initial condition. And then this every week, anytime it says every week or per week, that is a big indicator of the rate of change. So because it's not changing from one time to another, and it's always $5 a week. This is a linear relationship. And I'm going to take the $25, and then each week, I'm going to take $5 more, and that will give this total, I don't know what he's calling, maybe his savings. Okay, so savings. So $25 plus 5 per week will be the savings. And S is usually a bad variable to use because it kind of looks like a 5, but I picked it anyway. Some of you might have said something like this. You might have made a T table. You say, okay, so there's 0 weeks, he already has $25. And after 1 week, he's going to have 30. And after 2 weeks, he's going to have 35. And then some of you might have used this as an opportunity to see the relationship is plus 5, plus 5, plus 5. Anytime you have a constant rate of change like that, that will be a linear relationship. And you might have looked at an equation like y equals mx plus b to figure out the slope is 5 because that's the rate of change. And then the y-intercept you can see is right here of 25. Okay, so this is the initial condition rate of change way to look at things. This is the y equals mx plus b. Regardless, is it a function? Absolutely, because each x has only one y. After 2 weeks, he's not going to have two different amounts of money. He's going to have exactly $35. Okay, so again, this is what I was just talking to you about a little bit. The rule could look like this. The average rate of change here is the same as the constant rate of change. It is the slope. So the rate of change here would be the slope, and that would be 5. And you're talking about a rate. It's $5 per week. That is the rate of change, and all slopes could be thought of like that. The initial condition will always be your y-intercept for linear relationships. And the initial condition is $25 or 0, 25. This rate of change will never be different. It is a constant rate of change. So that tells you that it will be linear and that the slope will be the rate of change because it doesn't change from one value to the other. Because it's a constant rate of change of $5, it will be a linear relationship. Okay, here are our objectives. By the end of the lesson, we're going to be able to determine if a function is linear and then do it with some numbers, algebra, and graphs. Okay, so you've all seen this equation before. Y equals mx plus b. This is called slope-intercept form. And every equation can be written this way. It is most math teachers' favorite way to write a line because whenever students write it in slope-intercept form, there's only one way it can look, so it's really easy to grade. All equations can be written this way of a line as long as you know the slope and the y-intercept. I frequently tell my kids all you need is m and b. If you can find m and you can find b, then you can write the equation of a line. But what do these values represent? Well, m is slope and b is y-intercept. But what does that do? If I give you a number like 10 for b, do you have a picture in your mind of what that looks like? If I say m is -3, do you have a vision in your head? Because you kind of should, especially by the time you're in Algebra 2. So here's a nice little slider for you to look at. So you can experiment with these different values. So what happens here? Here's the equation y equals mx plus b. If I move b up and down, that's where that y-intercept is going. So if you want to think of it as the initial condition, you can. So the initial condition here would be 5. And then if I add a slope to it, that's a slope of 1/2. The slope of 1 is the one that you really should know. And if it's at direct variation, like we talked about, the slope of 1 is a 45-degree angle. So anything greater than 1 would be a steeper line. Slope is a measure of steepness of a line. If you go between 0 and 1, and they don't let us get that far between, they're only letting us do 1/2, unfortunately, it gets less than 45 degrees. And then when you hit to the negatives, then you are looking at a negative slope line. Okay, and you can just move the slider up and down. The steepness doesn't change on this one because the slope is not changing, just the y-intercept, and that moves it up and down. If I move the slope and not the y-intercept, it just adjusts the steepness. So let's practice graphing. This is in slope-intercept form. All you need is m and b, and you can basically do anything you want with a line. Okay, b is the y-intercept. I also used to tell my students, let's start at the very beginning. So we start here with the y-intercept because that's a very good place to start. It's a nice place to start with our y-intercept, our initial condition. If x is 0, the y-intercept is 3, and that is a good place for a starting point. After that, you'll look at your slope or your rate of change. And the slope here is 2. And you remember the rate of change formula is the change in y over the change in x. So it's really nice to have a fraction here. So because 2 is a whole number, it is rational, we can turn it into a fraction by putting it over 1. And this is telling you from this point, we're going to do a vertical change or a y change or a rise of 2 in a run of 1, and it's a positive slope. So it's going to go uphill. Now, I'm off the charts here, but you can go in the opposite direction and down to left 1. And then you have your line of y equals 2x plus 3. And remember what this is really telling us. Y equals 2x plus 3 has so many things that make it true. If I say take a number, double it, and add 3, what do you get? It all depends on what number you start with. So you can make that XYT table, and if I start with 0 and I double it and add 3, I get 3. If I go to 1, 2 times 1 is 2, 2 plus 3 is 5, and that point is also on there. What if I would have picked 0.5? Well, 2 times 0.5 is 1. 1 plus 3 is 4. There's points in between these other points. There's actually infinitely many. If I picked 0.6, that point would be on there. This graph is a picture of all the solutions that if you double a number and add 3 of what the two numbers could be. So a picture of a line is a picture of the solutions. Now, this is the form most teachers, I even talked to Mrs. Thurston about it, don't like as much, but the textbooks love to write it this way because it avoids using fractions. So this is called standard form. Different textbooks have different rules for standard form, and this is why I was talking to Mrs. Thurston about it. I knew that a lot of textbooks want this A value to be positive, but some of them don't require it. But what I didn't know is that the greatest common factor had to be 1. So what they're saying here is that if it was 2x plus 4y equals 8, they would say that is not standard form. They would want us to divide everything by 2 first and have x plus 2y equals 4. And I think all of us understand that, but I thought they were both considered standard form. This is the first time I've seen that addition to the definition. So A, B, and C, they said cannot be both 0. A and B can't both be 0. Otherwise, you don't have a line. You would have 0 equals C, and C is another number. So it would be like 0 equals 5, and that's not true. So only one of the things could be 0, or none of them could be 0. And X and Y are mandatory. You have to have an X and a Y. And then this A, B, and C's are just numbers. So this Y equals 2x plus 3, we can rewrite it to follow these rules. We need to get X and Y together. So let's subtract 2x here. And I would have negative 2x plus y equals 3. This does not follow my rules because they said that the first one has to be positive. So in order to make a positive, what I can do is I can multiply every little piece by -1, and that gives me 2x minus y equals -3, and then this would be considered standard form. Now, if I was to graph it, I would like slope-intercept form. We call that ready-to-graph form, a lot of us. It's so much easier because you can see the slope and the y-intercept. But this method is a little bit, it's not good for much. It's good for writing equations sometimes with linear combinations, which we'll talk about in a minute. But it's nice because there's not any fractions involved. So the activity of going from this to that form rarely ever happens, but frequently we go from standard form to slope-intercept form. And that's what we're going to do next. Here is a nice standard form equation. And if I wanted to graph it, the first thing I would want to do is I would want to change it to y equals mx plus b. Although in this particular example, that's not actually the best way to graph it because 2, 3, and 6, since they are all related, you could actually graph this one by the intercepts, we call it. And graphing by intercepts is one thing that standard form is decent for. And what that does is you plug in 0 for x, and it's really easy to see that 3y would equal 6 and that y would be 2. So 0, 2 is a point on this line. And if you let y equal 0, you would get 2x equals 6, and you would divide by 2. And 3, 0 is a point on the line. And since you only need 2 points to make a line, over 0 up 2, and over 3 up 0, that's actually a pretty fast way to graph it by the intercepts. But sometimes, like on our last problem, if I would look at the intercepts, you would get fractions. And I don't know if they're going to let me go back here. And fractions are not as easy to graph. So we usually would not choose that there. Okay, so if I would have got y by itself, because that's actually what the exercise is telling us to do, we would first move the 2x. And we would have 3y is negative 2x, and this will be a positive 6. To get y all by itself, you divide all the pieces by 3, and you will get y equals negative 2/3 x plus 6 over 3 is 2. Now you can graph it because you would start at the very beginning, the y-intercept, which would be 0, 2, because if I plug in 0 for x, I will get 2. And now my slope, which can be found by right in front of the x, is negative 2/3, isn't a fraction. So the change in y, or the vertical change, or the rise, will be negative 2, and the run will be 3. But the vertical change is negative 2. That's telling us to go down 2 and over 3, and that's just where that other point was a minute ago. You could do it again, and you can connect the dots, and you get that same line again. Take a look at this example. X plus 2y equals 16. I totally could do the intercepts again. If I did xy, if x is 0, what would y have to be? 8. If y was 0, what would x have to be? 16. I could plot those 2 points and graph the line. Or I could get x on the other side with the number, get y by itself, subtract x, 2y equals. Now, it's usually best to put the x in front. It's a negative x and a positive 16. Divide everything by 2, each and every piece, and you get y equals, remember there's a 1 here, negative 1/2 x plus 8. 0, 8, that y-intercept would show up right here, and then the slope is negative 1/2, which shows up in front of the x. You also could have used those 2 points and found the rate of change that way. You could have done y2 minus y1 over x2 minus x1, which would be 0 minus 8 over 16 minus 0. Negative 8 over 16, sure enough, simplifies to negative 1/2. So there's a couple routes you can take on these problems. Point slope form. Point slope form is kind of cool because it basically treats a line like all the other functions we'll learn about later this year. We're going to learn about parabolas. We're going to talk about absolute values and square root functions and cubic functions, all these cool graphs. And what point slope form does is it allows you to take a point on a line, which will be found at x1, y1, and then move it around so that it's a little bit different than the standard direct variation equation from 0, 0. So what we will do is we can take a point and move it left, right, up, or down, and the slope would be the stretch factor. Okay, so how does this work? Well, in this example here, the point, what would the point be from this graph? Well, the point would be x from the x parenthesis, y from the y parenthesis. And you're going to have to change the sign on both of these. You see how it says x minus x1? So that means that 1 is what the x coordinate is, because x minus and then x1 would be 1. The y coordinate of the point would be y minus, the y1 is right there, so that will be 5. The point on the line is 1, 5. What is the slope? Well, the slope is 2, or 2 over 1. So you can graph this by using the point over 1 up 5, and then sloping from there, or rising to run 1 from there. Or you could go down to over 1, and you can see where that y-intercept would have been. Okay, so this is a point slope formula. What if you wanted to make it look like y equals mx plus b? Well, we could clean it up. What you would do is you would take the 2 and you would distribute. And you would get y minus 5 is 2x minus 2. Get y all by itself by adding 5, and y equals 2x plus 3, which is the exact graph I have here. 3 is the y-intercept, and there's the slope. So you can graph it from the equation if you understand that this is the 1 and this is a 5 as a point, but many kids don't remember this formula very well. So many kids, when they see it in point slope form, immediately go to rewriting it in slope intercept form. Okay, how about this one? What will the slope intercept form of this guy be? Well, y minus 2, we can distribute, is 3x plus 3. Get y all by itself by adding 2, and you get y equals 3x plus 5. So the y-intercept would be the point 0, 5, and the slope would be 3, and you could easily graph it. So let's practice identifying some graphs. Which one of these graphs is 5x plus 5? Well, what do you know about this equation? You know that y is by itself, so it should be in the form mx plus b. And the y-intercept will be 5, the initial condition. So that's all you really need to know to get this question right. The steepness of all of them is the same. All of these graphs have a steepness of 5. One I don't believe is more steep than the other, although this one might be. They might be a little bit different than steepness, but they all look pretty close to a steep slope. So if I can find the y-intercept of 5, that one is not it. This one could be it. It's going by 2s, 2, 4, 5 right here. And this one is like at 1. This is the graph of y equals 5x plus 5. You would need to be careful with the scale to make sure you didn't mess that up. All right, so which one of these guys are lines? Well, what are the rules with lines? Well, lines can be written like this, or lines can be written like this, or lines could be written like this. The one thing that is certain is that there's an x and a y in all of these in some different numbers. So, is this a linear relationship? Well, if you subtract 5 from both sides, you'll get 2y equals 8, and y will end up being 4. Is y equals 4 a line? It is a line. It's a special line. It's a horizontal line. So this one is a linear relationship, but that was a little tricky way to start. How about this guy? Is this a line or a linear relationship? And the answer is no, because none of these formulas have an x squared in it. How do you feel about this guy? Y minus 5 is 2, x minus 1. This looks just like point slope. This definitely is linear. This one you might not like as well, and it's kind of confusing. What you can do is you can work on getting y by itself by multiplying everybody by 2. That would give you y equals 2x plus 14. And how do you feel now? You should feel better. This is a line. It just needs to get y by itself. X equals -4 is also a linear function. It is not a function at all, excuse me, is a linear relationship. But this is not a function because it is a vertical line, but it is linear. So this is what we call a special one as well. So be careful with the special ones. They are still lines, but the x equals -4 is not a function. Let's practice modeling. Okay, so this means setting up equations. And this is a good linear combination type of problem. And what does that mean? If they tell you two facts, and they're telling you some sort of total, linear combination is a good route to write this equation. So what you can do here is you can say a child's ticket costs $6, an adult ticket is $9. So how many different combinations could I make to get it to be $1,500? Some of you might make a nice little chart or an XY chart, and you could start playing around. You could say, okay, if I have, let's say I just sold no kids tickets. How many adult tickets will I need to sell? Well, you could take 1,500 and divide it by 9. And well, that's not what's going to happen because that would have to be 166.6 adult tickets. Can't do that. So that's not a combination we can use. What if I sold one kid's ticket? So if I had $1,500 minus the $6 and now divide that by 9, that would work. If I sold one child's ticket, I can sell 166 adult tickets, and then that would be $1,500. And you could keep doing this until you find a pattern. But because you're taking the child's ticket times 6 and adding to it $9 times the adult ticket, this is called a linear combination. 6 times the child plus 9 times the adult, and I want it to equal 1,500. Well, I can change this to x and y. And now I can solve for y to get an equation. This is in standard form, and it's good. That's good enough. If you were needing to graph it, though, you would subtract 6x, and you would get 9y is -6x plus 1,500, and you would divide everybody by 9, and you would get y equals, well, -6 divided by 9. We can simplify that fraction to -2/3 x plus 1,500 divided by 9. If you hit math 1, we already talked about that y-intercept would be 166.6 repeating. We're going to change that to a fraction of 500 over 3. This is the equation of the line that would model this situation. But you know you can't have 166.6 tickets sold. So in this case, after you graph the line, what you would do is you would look for what we call our lattice points, or the points that are real nice on the corners with integer answers, and those would be your solutions. And your table could help you find that. So I'm going to actually go ahead and show you how to use your table for this. I escape out of here maybe. Okay. It's loading up here. And I'm going to type in my y equals, I'm going to type that equation we had. So my screen is going to be a little bit messy because I need to write this down, but y equals, clear that out. So it'll be -2 divided by 3, that'll be x, plus 500 divided by 3. So if I hit graph, my zoom is messed up. So I'm going to hit zoom 6 to get my normal zoom. And you can't see anything. Well, why can't you see anything? Because my window is messed up. This is only from -10 to 10. So I'm going to change my window, and I'm going to start at 0 because I'm talking about tickets. And let's say that maybe I even sell up to 200 tickets. And let's start at 0 for y, which is the other tickets. And let's go up to 200 or so for there as well. Now, if you hit graph, there is that line that you can make. And I didn't go over far enough for my x. So go back to my window. Let's go over to 300 tickets for my X max. And that graph looks a little bit better. So what would the answers be? Well, if you go to second graph, that's where the table is. And the combinations that will work would be like this: 1 and 166, 4 and 164, 7 and 162, 10 and 160. Those are what I mean by lattice points. Those are the nice points that would work out for your equations. So which graph shows the relationship? And we got it all by itself. And we graphed it, and it looked like it went all the way over to 200 here. And suppose all on this day, all tickets were kids' prices. Okay. So what if it was all kids and 0 adults? Well, if it's 0 adults, I would just put 0 in for Y, and you could take 1,500 divided by 6, and you would see that there are 250 kids tickets sold, and that is actually the value that's right here, or that x-intercept. So if you had 250 kids tickets, you would get your amount, and that's called the x-intercept. The y-intercept here didn't work because it did not work out nicely. Okay. Initial condition rate of change problems. And those can be told, like I said, it'll tell you a starting point and then some sort of rate of change. And in this example, it says an airplane is 30,000 feet. That is the initial condition. It is descending 1,000 feet each mile. That is a rate of change or a slope. It's always descending at that pace. So it's a negative, it's going down 1,000 feet per mile. And then that will tell you the height of the plane. So that is the equation. You could rewrite it as negative 1,000 m plus 30,000 equals h. You could change this to x and this to y if you want, and you could graph it to take a look at what's going on. Okay, this looks like the last example before I summarize things up here. Which form is this? This is that point slope form. And it's talking about the cost of an order of widgets and the number of widgets ordered, okay? So we're going to choose what's happening here. Well, what does the 3.25 represent? That is the slope. That is the rate of change. So if you're talking about widgets, what are you talking about with the 325? 325 each, that sounds like a rate of change. Is it a flat shipping rate? No. And this one say a flat shipping rate. No, that's not what they're talking about here. The widget's rate of change is 325 each. They do charge a flat shipping rate on all orders, but they didn't tell us what it is the way it looks. But what they did tell us that if it's 15 widgets, the cost would be $53.75. If you wanted to know what the flat shipping would be, we would have to clean this up. And you would have y minus 53.75 equals 3.25x minus, I didn't give myself much room here, 15 times 3.25, 48.75. Okay, so then we just add 53.75. So I have a negative 48.75. I'm going to add to that 53.75, and I get y equals 3.25x plus 5.3. This is the flat shipping cost, $5.30. This is the rate per widget. The 15 and the 53.75 was a particular example, a point on the graph where 15 widgets cost this much money. So in summary, all the things we talked about today, we talked about all three types of equations of lines and their different properties. And we talked about how you can tell from a graph if it's a line. If a table has a constant rate of change, a plus 5, plus 5, plus 5, then it's linear. And if you can write it in one of these forms, then it is a linear relationship. And you know how to graph from slope-intercept form by finding the beginning, the y-intercept, and then doing the rise over the run, and completing the line. Okay, so that's it for linear relationships and linear functions, and we'll talk a little bit more about writing equations of these on our next lesson.